It's a pleasure to have you.
Thanks so much for thinking of me, Xavier. I'm really happy to be here and like connect with a lot of people, who I've not chatted in for a while. And yeah, thanks for this extremely gracious introduction. And let's get started. So for context, I'm from Montreal, which is actually quite close to Cambridge. So yeah, it's to the south and east of Canada, as you can see. And this is our group. This was back, 2 years ago. We haven't had a group photo over the last year or so, but yeah, it's a pretty small group doing robotics at the University of Montreal, but it's actually part of a larger umbrella, which is Mila. So Mila is this really big group, and you have like subgroups that do robotics, graphics, generative models, theory, and a lot of other cool stuff. And yeah, even this one was even before the pandemic, I guess 2018 or so, and Mila's only been growing. So just to give a brief, sampling of all the various things that I like to work on, one subset of approaches that I used to work on a lot, especially during my master's, was perception for autonomous driving. And let me just get a pointer. Okay. And a lot of my work still revolves around state estimation and mapping for robotics. But my primary research area, particularly over the last 2.5 or so years, has been trying to build differentiable variants of, a variety of processes, particularly targeting robotics, graphics, and physics communities. And in this talk, since there's a vision reading group, I'll focus on my efforts towards differentiability that are particularly relevant to computer vision. So before I start, like this talk was titled Building Differentiable Models of the 3D World. So I'll just try and unpack the various terms I use here just to provide context for what's to follow. And at any point during the talk, if someone has a question, please feel free to post on chat. But probably the better way is just speak up and interrupt me because I might not be just paying attention. And if at any point, a slide is stuck or an animation doesn't play, just holler and I'll try and see how that can be fixed. Yeah, so I'm particularly interested in applications that involve robots operating in 3D. There's autonomous driving, manipulators, and all of the domestic robots. And typically, there's been a divide in the robotics community as to how to go about executing tasks. On the left, you see like the model-based paradigm, roughly, which tries and builds these high fidelity representations of the world. And once you have these representations, you can plan and act on them. And on the right, you see the model-free variant, where you just go from pixels to torques, as they popularly call it. You're just given images or very low dimensional representations, and then you directly output an action command. So this talk is largely geared towards the model-based paradigm. And then towards the end, I'll probably briefly touch upon, how these two communities might interject. So if we just look at how classical robotics or embodied agents have evolved, the classical robotics pipeline over the last 2 or 3 decades or even more, and still most industry pipelines have been, you have a perception module, a planning module, and the controller. And the perception module builds a model of the environment, which is fed to the planner. And then the planner generates a plan, and you have a low-level controller. And this is not a linear process. There can be a variety of feedback loops interacting in various ways. But this is how classical methods are. They're very compositional. And on the bottom of the slide, you see like learn techniques, particularly model-free methods, where you just have like inputs, particularly observations or perceptions, and you directly need to regress to an action. So what I'm trying to argue for in this talk will be, can you impose structure within this monolithic modules? And that structure is usually induced by differentiable variants of perception processes. This talk is particularly focused on perception, being a vision reading group, and yeah, how you can actually leverage these differentiable models to solve a few meaningful tasks. And what I mean by differentiable, I guess a lot of people are familiar with the notion of computation graphs. If you've used deep learning frameworks like PyTorch and TensorFlow, you've used computational graphs without realizing you did. So if you can compose like whatever operation you want to do, if you can break it down into atomic components which are individually differentiable, you can then compose them and backprop through them by applying like chain rule or like reverse mode or a diff. And this has emerged as a very powerful and flexible paradigm for modern ML. So we've been seeing a lot of work, particularly from 2015 and onwards, on various ways of using these differentiable modules. So you see differentiable optimizers, physics engines, and rendering engines be used to solve like perception tasks and a lot of other tasks in the ML community. In this particular talk, I'll focus on two recent approaches that I worked on, and they're both very similarly titled. So just so that you're not confused, GradSlam is a differentiable 3D mapping or SLAM framework, and GradSim is a differentiable simulation framework. So this is what I'll be covering in today's talk. And yeah, based on how we are time-wise, I might choose to skip a few of the implementation details in favor of like conveying the broader take-home messages. Again, like at any point, if you want to just interrupt me, ask questions, I'm happy to take them in between as opposed to just waiting till the end. So yeah, the first piece of work I want to talk about is GradSlam. And the paper is titled DenseSlam Meets Automatic Differentiation. This joint work with Ganesh, Soroush, Derek, and Liam. Soroush and Derek actually joined us after the project, and some of the results I'm going to present have their involvement. And yeah, so just a one slide intro for anyone that's not really familiar with SLAM. SLAM stands for Simultaneous Localization and Mapping. So you want to build a representation of the environment while simultaneously localizing, in this case, a camera within the representation that you build. And this particular talk will focus on DenseSlam, which means you're trying to represent every pixel in every image in a dense 3D representation. So the dense 3D format could be a mesh, a point cloud, or whatever, but that's the broad context here. And typically, it's not been clear as to how you can apply deep learning for a problem like SLAM. There's the inherent like sequential assumption here. You can't treat SLAM as an IID process because the sequence really determines how you get your observations. And the more important reason, it's very heavily engineered. So you don't really know what you want to learn here. Like, do you just want to feed all observations to your neural net to predict like camera poses and a map, or do you actually be smart about it and learn only the parts that actually need to be learned? And because of this, traditional SLAM is still yet to see like the deep learning revolution in there. So just to give you a broad idea about how a typical dense SLAM system might look like, the real key idea of GradSlam is you can treat SLAM as a function that maps a sensor data stream S to like a state estimate M, and M is just trajectory of the camera and a dense map of the environment. If you actually view this function as a differentiable operation, what that would mean is if you perturb your sensor data by tiny like delta S, your map will change by the gradient of SLAM with respect to delta S. And this is the one slide key idea of why we want to do GradSlam. So you can actually get how each pixel in this map contributes to, each pixel in every image contributes to the eventual 3D reconstruction. And that's an important property to have, which can aid in a lot of downstream tasks, a few applications of which I'll try and cover. So our first real attempt at this was, it's actually a quite naive attempt. We took a SLAM system and tried to implement this in PyTorch. And yeah, just to give you an overview of a dense SLAM system that we took, you have RGBD images and you perform surface measurements to produce the vertex and normal maps and so on. And you now reconstruct this surface to get a local map of the environment. And we assume you have a global map of the environment, which is initially empty, but as time progresses, you're fusing all of the local maps into a consistent global map. And the idea of SLAM is now to take this global map and reconcile it with the local map, try and align these and take the signal from the local map, throw the noise out, and fuse the signal with the global map. And our first attempt failed spectacularly because we realized a lot of these operations over here indicated red boxes that weren't differentiable. And we actually needed to figure alternate differentiable variants of these. And that's what we did for GradSlam. We took all of these non-differentiable components and tried and made them differentiable. I'll probably not go through all of these components, but for sake of time, I'll cover one component in a little detail. So there's nonlinear least squares optimization, which is a core component of SLAM. So if you want to reconcile multiple views, register depth images from two views, even fuse, it's all a nonlinear least squares problem in general. And as with any nonlinear, non-convex optimization, you do not necessarily have a unique global minima. So your initial guess really determines where you reach, and you're often far off from the global minima, which is why nonlinear least squares optimization tries and it tries to be a little smart about how you go about things. So techniques like Gauss-Newton, they actually leverage second order information or approximate second order information to accelerate convergence. So what this might mean is sometimes you could even diverge if you took really big steps. And you also have issues with singular Jacobians and a lot of things. So you can see a diverging case here. You just took up too big of a step. So what SLAM systems usually do to prevent this is they try and adjust the step size. So if you actually feel your step size is too big and you're going to diverge, you roll back and take a much smaller step, and you keep rolling back until you actually get to a feasible solution. And there's also a few other tricks that you use to damp this approximate Hessian system. And the damping coefficient ensures that J transpose J to the inverse is, J transpose J is not too close to being singular. So adding this tiny diagonal element helps stabilize things. But the problem with the LM optimizer that a lot of SLAM systems use is it's not readily differentiable. You can't get gradients with respect to, let's say, the lambda parameters because of the if-else style. If the cost function decreases, go ahead. But if it doesn't, roll back, try a smaller step. If it doesn't, roll back, try a smaller step, even smaller step. So what we do instead is we reparameterize this as pretty much like a sigmoid switch. You have this if-else case. Can you smooth it out and so that most of your density is concentrated either towards the if branch or the else branch, but not anywhere in the middle. So we come up with this reparameterization of the Levenberg-Marquardt algorithm, which we call GradLM. The key, I'll not go through the equations, but the key thing is the damping coefficient sequence. If you look at this, it's not differentiable. So all these parts, the function is constant, so you don't get a gradient. And then at the transition point, the function has different left and right values, so it's not continuous. But with GradLM, you get gradients at least in this smooth sigmoid style region. Oops, I guess slide stuck. Yeah, we also have a few like differentiable raycasting and mapping modules to support a few SLAM systems. But the key idea is now we ended up with implementing differentiable variants of two existing 3D reconstruction pipelines. And the accuracy of these pipelines were not really impacted by all of the design decisions that we had to make, smooth things out to make things differentiable and so on. And it works fairly well on real data. Real data contains a lot more noise. So there's some drift, but it works like reasonably well. But let me just quickly skip to why such a system might be of interest. Like, why would we care about this entire 3D reconstruction pipeline being differentiable? So here's one really cool experiment that that just really paved way for a lot of what followed. So we took a sequence of RGB and depth images. We passed them through GradSlam, and depth was actually noisy. So we ended up getting like a noisy reconstruction. And we'd compare this noisy reconstruction with a ground truth reconstruction obtained from like clean depth images and backprop all the way through to the image. And I'm not sure if you can see this really clearly, but the edges or like the prominent edges in the image have a very high gradient magnitude. And you see the stars kind of pattern in between. That's the camera frustum expanding out. So our intuition basically checks out that pixels that are closer to 3D regions that are sharp or discontinuous, they have higher gradient representations in the image. But now, if we just cut out this huge chunk, we just cut out a block from the RGB and the depth images. So this will create a hole in the reconstruction. If we compare this with the same kind of clean reconstruction and backprop, we get the gradients again. If we subtract these gradients, we get the occluder, which is basically the difference between the two image sequences. So it's like you can actually attribute the contribution of each image pixel to the 3D map. And here's like a very similar demo, but in this case, we create an occluder in front of the camera. And as we're moving it, we plot the gradient difference maps. And in all cases, like GradSlam is accurately able to identify what the occluders are. So now that we have this tight connection between a 2D image pixel and like a 3D reconstruction, we can use this to learn better 2D representations. For instance, like this is actually work by an intern at our group, Nikhil. He's he's an undergrad at IIT Dhanbad, and what he did was just take these RGB images, feed them in through a depth estimation network, and then like fuse them to GradSlam, compare with a true map, and then backprop. So what would ideally happen is this is your 3D depth, and as you keep optimizing, your predicted depth starts approaching the 3D depth. And this is much better than just learning depth maps via 2D supervision. So we actually have a few more results that we ran for longer in the paper. In this case, we put up both the RGB and depth images, and we try and recover them from ground truth reconstructions. And in most cases, we're able to recover very accurate, depths and colors, and also images, portions of depths that are missing in the initial depth map. So this depth map has no representation for this patch, but by pulling in information from the other views and like backpropping through the SLAM system, we're able to figure out what depths that these pixels might be. So we're like compensating for sensor data that might be corrupted or absent. Here's like, this is an interactive visualization. I'm not sure if you can see the gradients very cleanly here, but you basically click on a point and we backprop and see, what are the images that contribute to this particular point. And as you keep going back in time, you see that more of the image contributes to that point. This is because the receptive field of a particular point in the map tends to increase as you go back in time. So the key take-home messages for the first part of the talk is GradSlam is a very interesting way to assess the contribution of each pixel in a 2D image to the 3D map. And these gradients can help in learning a few, like learning of consistent representations across multiple views. And the downsides here are we require 3D supervision. So if you looked at the pipeline, we need these clean looking 3D reconstructions to be able to supervise and then backprop all the way. And the other thing is there are long unrolled graphs at times when you have 100 frames of video. You can't effectively backprop through all of those frames. There's also memory requirements, and there's issues with the quality of gradients themselves. So one way to rectify this, this is again a project by an intern at our group, Harsha. And the idea here is, can we just get rid of this 3D map requirement and instead have a differentiable renderer in the loop? So you have a bunch of depth maps and you want to fuse them using GradSlam into a consistent 3D map. And you want to render them out again, from the same viewpoints that you initially observed them from. And all of these things must match up because you're rendering the images that you just reconstructed. This still like just a one slide pitch for an upcoming work. So yeah, just a preview result. This is where we have like a bunch of frames and then one frame is masked out. You're using GradSlam to reconstruct a very noisy and messy depth map and using gradient propagation to recover the original image back. And a very similar idea can also be applied to material property estimation. So if you want to estimate like the diffuse and specular reflectances of a scene, this is probably like a good way to go about it. So at the bottom, you see like the true diffuse and specular reflectances, and on the top, you see like a randomly initialized map that's getting optimized over time. And yeah, the bottom right corner just has the reference to the reconstruction. There's also one issue that we're trying to address in the gradient explosion or memory footprint is to leverage implicit differentiation through like the GradLM pipeline. So the implicit GradLM or i-gradLM variant we're working on is basically an memory. So it's not memory intensive, and it doesn't require you to store intermediate activations. And importantly, it will not require the optimizer to be differentiable. Like we went through the pain of designing GradLM because we needed differentiability. But if the gradient computation won't depend on the optimizer, we can now use a full trust region approach, like a standard off-the-shelf LM solver. That's basically the first part of the talk, where I was talking about GradSlam. It was more about 3D reconstruction. Happy to take any brief questions before I move along. All right, so if anything, please feel free to interrupt me. But now I'm going to switch gears and talk about something slightly different. So this work, I'm going to talk about VSim, differentiable simulation for system identification and Visuomotor control. This is actually the first time I'm giving a talk on this topic. So, just a caveat, it might be a bit scratchy. This is joint work with, Miles Macklin from NVIDIA was an equal first contributor on this project, but there's also a lot of others: Florian, Vikram, Linda, Martin, Brendan, Jerome, Kevin, Kenny, Liam, Florian, Sanya, and Derek. So just to give you a brief idea of the problem setup, we assume we're given like this video sequence of like an object being acted upon by external forces. And we want to estimate physical parameters of this object, for example, mass, friction, and elasticity. But there might also be other physical properties depending on the nature of the object. For example, for like deformable beams, or we'll have other material properties like the Lame parameters and so on. So the key idea of the GradSim project is to explicitly model image formation and dynamics. So there's plenty of work that tries and estimates physical properties from video by using some form of supervised learning, and like having a model-free approximator like a ConNet or an LSTM or similar to, given an input video, predict what the properties are. Our idea was, can we actually bake in priors about how the dynamics of a scene evolve and about how the image itself is formed? So there's been a bunch of work in the ML community. I know that Yuan Meng is here. So Diff Tai Chi was a really cool paper that came out last year. And all of these ideas were based on the fact that you could model differentiably the evolution, the time evolution of a system, like by using a differentiable physics engine. So if you can actually build a differentiable physics engine, you can now backprop all the way from 3 states and figure out what the material properties are. And you could also do other tasks like control, not just system identification. Just to walk you through what the GradSim pipeline entails, we assume we're given like a representation of an object. We do not assume any information about mass, friction, or elasticity. We just initialize them to uniform random noise. But what we do assume is we have a geometric representation of the object, which could be like a 3D mesh. And we know all the external forces that are acting on the system. So that means we know the gravity, and we might know other forces that, for example, a robot uses to interact with the system. And we input this object specification to a physics engine. And this physics engine is differentiable, which means it produces states, typically positions and velocities. And all of these can be differentiated with respect to the parameters of the object. So the part that I've discussed so far, this is what a majority of approaches using differentiable physics engines do. So these states are the output of the physics engine, and you define supervision on the state space, usually 3 dimensions or 6 dimensions, depending on what kind of object you're looking at. And for deformable objects, the state might incorporate a lot more, because you need to specify the location and velocity of each point in the system for a few systems. So what we wanted to do instead was we thought this was quite limiting, because you can't always assume state supervision. It either means you have like an accurate motion tracking style capture system where you can place markers on the object, but there's also objects like deformables and cloth, which are almost impossible to track state of each particle. So what we do instead is we use a differentiable renderer that takes in the states and the object geometry and renders it out to like a predicted video sequence. And this video sequence is compared with the ground truth video. And we define like a loss, which is basically the MSE loss of frame by frame, pixel-wise L2 loss between the predicted and ground truth videos. Since this entire system is differentiable, we can now backprop all the way from the loss function to the object parameters, and we can get gradients with respect to the object parameters. And we just keep optimizing for the parameters until the predicted video nearly exactly matches the ground truth video. So there's like a few details about the differentiable physics engine, which I'm not sure I'll be able to cover in full, but just to give you a brief idea, we have like a scalar loss function with respect to the system parameters and the system state just comprises positions, velocities, and any other design parameters that you might have. And you could differentiate through this entire system by using the adjoint method. And this is something that diff tai chi actually uses quite a lot. So a tape-based automatic differentiation system. I'll just skip over the details and go to the high-level overview of how automatic differentiation is implemented in the GradSim framework. So we have 3 levels of autodiff. The bottom level is just primitives, vector and matrix arithmetic, and so on. And one level above this is a few kernels that are pre-implemented, let's say for time integration or for forward, backward pass physics simulation for a variety of objects and for evaluating forces, collisions, velocities, and so on. And perhaps the key difference between, let's say, a framework like diff tai chi and GradSim is that we have a top level autodiff, which is basically the PyTorch autodiff framework. So what we do is we have an interface that that just translates all of these mid and bottom level kernels to like PyTorch autograd functions, and you can actually just use this entire, the bottom and mid levels of the autodiff framework with PyTorch neural nets. This means that you can actually implement neural nets in PyTorch, and in fact, our differentiable renderer is implemented in a combination of PyTorch and CUDA, and this all plays well, and you get gradients all the way back to, let's say, the physical parameters, which is defined here. So there's like a very program transformation style approach to this, which resembles compilation. But I'll probably skip this just to keep the talk contained at the high level message. So yeah, the GradSim program transformation just basically entails that you define a very simple function like this, or here sine A plus AB, and this generates all of the code for you. So we currently have C++ and CUDA code generation capability. We've implemented quite a few physical systems in here. So there's rigid bodies, and we use like relaxed contact and friction models here. So you basically see like a rigid body. In this case, it's just a cube. And there's support for deformable tetrahedral meshes. So the thing with deformable objects is that they're solids. So you can't just get away by representing the surface. The graphics community or the rendering community cares a lot about how the surface of an object is represented. And in case of physics simulation, we care a lot about the internals as well. So these are now solid tetrahedral FEM elements and not triangles. And we use like neo-Hookean hyperelasticity model for like that's just a design choice we made, but there's like quite a few other alternatives. And yeah, we've just building on the tetrahedral FEMs. We have like a triangle FEM that can be used to simulate thin shell objects, like this cloth falling in the presence of lift drag forces. And there's also a few other physical systems like pendulum, mass spring dampers, and incompressible fluids, but these were mainly used for debugging the system. And yeah, the more cool applications are with the deformable objects and cloth. Our differentiable rendering engine is based off of previous work. So there's 2 dominant approaches for rasterization-based differentiable rendering. On the left, you see the soft rasterizer, and on the right, you see it's called DIBR, differentiable interpolation-based renderer. So both of these are rasterization-based. They're not necessarily, they don't simulate light transport. But we found that in our case, these work quite well, particularly because we're working with simulated videos. And just to put it all together, just remind you of the pipeline, we have this differentiable physics engine based on source code transformation approach. And then we have this renderer, which predicts a video. You compute an L2 loss pixel-wise with respect to the ground truth video and then backprop all the way. So here's a few results on a rigid body parameter estimation. So this is a cube that's falling under the influence of gravity and an external force applied to it. So before optimization, the mass of the cube, etc., the cube's deemed much heavier than it is, and after optimization, you get to like an accurate estimate. You also see that it's important to be very precise in parameter identification, because if you get the friction coefficients or other contact parameters wrong, you might often just have very unobservable or like very minor differences in the end state. So we're actually able to recover even these tiny differences quite well. And here's like a deformable solid example. This example is actually based off of an autograd and example, and I guess Diff Taichi also has a very similar example where we have like this target pattern. This is just an image that I got of Google Images and then ran like an off-the-shelf binarizer, one that you could find in any open source library. And the target here is you want to actually simulate all of these particles to evolve to match this target pattern.
Just a quick question. So you say that the fluid is incompressible. So is that really incompressible, or is something that is weakly compressible, or something that is close to incompressible?
I'm not sure. I follow.
Oh, okay. Yeah, like if we want to do something that is strictly incompressible, then we probably need to do something like the real adjoint method, which is slightly more complex.
So yeah, we don't have any, let's say, no vorticity confinement constraints and so on here. So yeah, that's still, a hand wavy assumption here. Agreed. Thanks for bringing this up. So yeah, the loss landscapes through GradSim were remarkably smooth. So this is the loss landscape if you're looking at mass estimation of a rigid body. This is the ground truth mass, and even if you're sort of far off from the ground truth mass, the loss landscape is somewhat smooth. And this is similar, like loss landscape for the elasticity parameters of a deformable solid. So one sort of comparison that we did was, what if you take a non-differentiable simulator and then just apply gradient estimation to it? That's just a naive way of making any simulator differentiable. But we found out that it was actually quite tricky to even just do mass estimation. Like it's a single scalar parameter with a pi estimation using reinforced. I'll skip over these tables because these are all in the paper, but yeah, they just say we do quite well, and I think it's worth reading them in the paper. But here's like a deformable solid FEM example. So over here, we're now trying to do control. There are these tetrahedrons in the GAIR that you see, and you can actuate these tetrahedrons by expanding and contracting. So if you expand a tetrahedron, you can just, if you expand the right set of tetrahedrons, you can get the object to move. And the target now, so the way this is trained is you have a 2-layer neural net that tries to give you the actuation magnitude for each tetrahedron. And you have a ground truth image. So the ground truth is just an image. And the target for GradSim is at the end of the episode, I think it's 3 seconds or 4 seconds here, you need to, this GAIR should roll over to the ground truth position. So it's actually quite interesting to us that you could just use this one frame as supervision, and then you can figure out what are the controls that you should apply in order to reach here. So just before I move further, Xavier, could you tell me how we are time-wise? Could I take 2 or 3 more minutes?
Yeah, absolutely. You can take 5 minutes and yeah.
Sounds good. Thanks. So similarly, we have an experiment for cloth, but in the case of cloth, what we do is we try and predict the initial velocity with which you throw the cloth, and it basically needs to approximate this ground truth image on the right. So the supervision here is not a sequence of images, it's not a video, it's just a single target image. We've also tried like supervising in various schemes, using more images and using a much denser sampling of the video, but we thought this would be a cool application to showcase if you can do this just using one image. The caveat though is using one image, it takes much longer compared to using an entire video sequence. And it also requires tuning the parameters of the renderer so that the gradients from this silhouette actually backdrop or are non-zero over this entire image region. So as one other experiment, this is actually inspired by the diff Tai Chi walker experiment. We have one target image of a walker. So it's just like this table that you see here, table-like object. This one is in 2D, and just like the tetrahedrons, you can make this walk by expanding and contracting triangles. And what we do is VSim has a 2-layer neural net that initially produces random activation. So you can see that it's not doing anything fun. But the target is at the end of 3 seconds, we need the target to be here. Like we need the walker to match that target image. And in this scenario, it was actually quite interesting to see that we could learn even in the very first iteration, the silhouette, the renderer comparison tries and pulls the object or the walker towards the target. And at the end of 3 iterations, we're actually able to walk quite well to the right. We also did an analysis of imperfect models. So what would happen if your friction were actually not modeled, or if your object is actually rigid, but you model it as a deformable object, and so on. And we had a few interesting comparisons there. I'll skip this for now, but I'll encourage you to take a look at the paper. And another experiment we did was how important are shading and texture cues for performance. Like, does it work if you just use color, or do you actually need texture and shading information? So in general, textured variants perform much better than shaded variants, and both of these perform significantly better compared to like the only color variants. So there's no shading involved. So the take-home messages for VSim for this part of the talk are, it's actually quite interesting to see how you can estimate physical parameters entirely from video. For example, in the walker, it is very interesting for us to see that you can actually make the walker walk to the right just by giving a 1-frame image as loss. And this might open up a lot of interesting ways in which you could leverage differentiable physics engines via like differentiable rendering, like not trying to operate on 3D supervision. So not requiring 3D state is probably a key to make this operate on real world videos. So the downside is we don't get to real world videos yet. We're still operating in simulation, as you largely see here. So the sim to real gap needs to be overcome. And the other sort of key point here is, as someone said, all models are wrong, but some are useful. So modeling imperfections can really impact your performance. So this is a bit of a trade-off on how much do you handcraft and how much do you learn. And in case of a differentiable simulator, it's as though you're handcrafting a lot of things in the system. So just as a 1-slide summary of the entire talk, differentiable models, they're not just cool, like people are working on them because they're actually quite useful in a few real world tasks. And the structure usually seems to improve learning, make learning faster or efficient. But The downside is they're still not perfect. You need to figure out how best to integrate these models with model-free approaches. So there are actually interesting proposals coming up in the community as to, can you actually learn just the parameters within a differentiable simulator that actually need to be learned? And for example, can you just learn contact models, or can you augment neural simulators, or like, can you augment differentiable simulators with learned residuals that can actually help you generalize the videos? So that's really the take-home message. Differentiability helps, but we also need to see how this gels in with the model-free paradigm. And yeah, at this point, really happy to take any questions you might have. That's all I had for the talk.
Thanks a lot, Krishna, for the really great talk. That was very exciting. We have some time for questions. So maybe I have a maybe slightly related question. I mean, in all these works, I guess your input is like pre-made, like static video or static data set, right? But I guess that using the simulators also opens the possibility to say, maybe like use them to conduct experiments that allows you to learn more about the world, right? And maybe like, yeah, a given video doesn't give you enough information on material properties, but if you touch the object in a different way, you could get more information. So I'm wondering if you have thoughts in integrating those to kind of like embodied systems that can like get more information.
Yeah, that's actually a really cool suggestion. Like the way VSim operates is it's passive. You don't really get to interact with the environment. You're given a video sequence, but active techniques for system identification can actually help quite a lot, particularly in not all video sequences or demonstrations are equally useful. So by explicitly learning how to interact, you might be able to come up with efficient ways to identify systems. And there might be systems with, let's say, symmetries or so, where the video might be confounding. I'm guessing for these, you really need access to the system so that you can choose what kind of views to query.
Thank you.
It's really nice to see a combination of differentiable renderer and differentiable simulator. I do have a question regarding the system identification task we are working on here. So basically, when you're using a differentiable renderer, then I believe you're computing a loss on the final image of the current simulation and your target simulation. So I think one issue is that let's say you have if the object you render in the current simulation doesn't even overlap with the target image, is that going to generate a zero gradient on the loss function? And how do you deal with that situation? Do you use something like Earth mover distance to maybe get a something that is useful for the gradients?
That's actually a good question. And to give you a bit of an anecdote, that's something we did struggle with initially in the VSim project. So we initially took maybe a very weird physical system simulate. We were thinking about simulating a billiards table. So in that case, what we figured was the initial overlap between the billiard balls that was crucial for the renderer gradients to seep through. And if the data association is somehow incorrect, then you get incorrect transport of gradients. So the ways I can think of the top of my head to overcome them are actually use like an additional segmentation or data association module. I guess it's hard to solve both these problems in conjunction. So maybe assume you have a fair solution to that. The other sort of like you raise a very good question about, are the loss functions that we use for differentiable rendering even sensible? Like pixel-wise MSE, when you know that you might be comparing two very different quantities. So yeah, like I've given a bit of thought about it, and there's really cool ways maybe to explore what the loss function should be. Like, could you even learn loss function, for example, by just having something like a discriminator decide whether a sequence is valid or invalid?
I see. That makes a lot of sense. we have one project on doing this kind of estimating something like the distance between the final configuration, and we did find Earth mover distance to be a great fit there, because sometimes like if we're just doing some pixel-wise comparison, essentially the gradients can only come from the edges, and then it can be an issue if there is no overlap at all.
Yeah, and the other thing about MSE laws that a lot of people might not immediately realize is if an object is towards the edge of the image, then the laws will just try and pull it towards one of the edges or one of the corners, because you have more pixels in the source image compared to the target image. So the optimal solution is to just push this out of the scene, as opposed to like trying to bring it in.
I see, that makes sense.
Hi, Krishna. Quick question.
Hi.
So I was curious for some of your examples with the, for example, the cloth and even the ball moving and these types of things. Is there a sense for what the space that of the solutions could be? Like how I'm assuming you had some kind of prior or some kind of constrained search space, or how did you kind of deal with that?
So that's right. That's another good point, which I should probably have highlighted in the talk. So as with all differentiable like simulation approaches, we are somewhat sensitive to the initial guess, and differentiable renderers or simulators are not a silver bullet in this context. If you're actually far off from your distribution, you don't do really well. But one guide that we found was to use a loss landscape as a guiding mechanism to decide what our parameter ranges should be. So we actually know that for masses, for example, we're actually quite, we have quite leeway for initializing incorrectly. But for other parameters like elasticity, the loss landscape tells us we can probably do a range of 0 to 1,000 for, I don't know, the Lame parameter or so on. So we try and restrict, clip things to fit that particular regime. But our initializations are almost always uniform. So we just pick like a random value in that interval and initialize.
Okay, got it. And I could also imagine that, so if you had a few parameters that, I guess there's joint interactions between them, and so this could potentially make it more difficult when you're actually doing your descent or whatever, because it's a very specific combination of these parameters that actually give you your final result.
That's right. So if you think about, let's say, if you want to optimize for the geometry as well as elasticity parameters of a deformable object, you'll run into some very similar issues, because you don't know an approach that a lot of people follow is initialize with a cube or a sphere and then deform that to like whatever object you have. So differentiable renderers, the way they're usually applied for single image 3D reconstruction is you start with a sphere or an ellipse and then deform that sphere or ellipse until you get like the object of interest. If you were to do geometry estimation in conjunction with like physical parameter estimation, I guess you'd run into some of these issues. And we actually did encounter a couple issues when trying to simultaneously solve for geometry and physical properties, which is why I guess the assumption that I made in some of the first slides was we assume we know the geometry of the object. That still is a limitation that needs to be worked on.
Got it. Thank you.
Okay. Yeah, that is it. Thanks so much, Krishna, again for your talk. It was great hearing about this work.
Thanks. Yeah, it was great being here.
Yeah.
Yes, thank you. Thank you for your visit.
Thanks, Antonio.
Bye.
Goodbye.